us continue our discussion on inventory by looking at inventory models where the demand varies with time. So far in all the inventory models we have made two assumptions. One is that the planning period is infinite. So, we have an infinite planning period, and second is demand is the same or constant and uniform demand. For example, when we looked at the basic inventory model, which is the sawtooth model, and when we said we start ordering at Q, at time equal to 0 we order a Q and it is instantaneously replenished, and then it is consumed till the inventory reaches 0, and then another order is placed, and then this process continues. Now in this we assume that this is going to go on forever and we are planning for an infinite period, and because we are planning for an infinite period, to evaluate the total cost we take a certain fixed period like a year, and then we try and optimize the value of Q for which the total cost is minimized. The other important assumption is that the demand D, which is the rate at which the inventory is falling, the demand D is the same at every period. More importantly, it is the same at every instance. Now what happens to inventory problems when the demand varies with time, which is a very practical thing that happens around. Production quantities are different in different periods because demands are different for different periods, and once the production quantities are different for different periods, the amount of material required to make them would also be different, leading to inventory problems where the demand varies with time. So let us take an example and try and explain a few things about time varying demand. So we take an example where we assume that we have demand for 12 months and these demands are 400, 600, 1000, 800, 1200, 900, 800, 1000, 1200, 700, 600 and 800. Now these numbers have been taken such that when we add all of them we get 10,000. So now we assume that the annual demand of 10,000 is now split into 12 monthly demands of this. Now several questions are there. Now like in the earlier models, are we going to have the same order quantity or is the order quantity going to be different, or like in the earlier models are we going to have the same order frequency or is the order frequency going to be different. So we assume here again for the sake of comparison that order cost is rupees 300 per order, inventory holding I is 12%, sorry, inventory holding I is 20%, inventory holding I is 20% of unit price C, which is also rupees 20, so that CC is rupees 4 per unit per year, which is the same number that we had assumed in our earlier examples and illustrations. And as I mentioned, the other difference is we are considering 12 months or 12 periods. Now each period is a month and our planning stops at the end of the 12th month. So we are not looking at the 13th month demand in this particular situation or illustration. One of the ways of solving this problem is by using integer programming, and the motivation for that comes as follows. Now if we take this month's period and this month's period, now we could either order 400 which would meet the demand of this period. Let us say we order 500. Now what happens is, if we order 500, then we order once here for 400, we order a quantity of 500, which is out of which 400 is consumed at the end of the month, and there is 100 remaining at the beginning of this month to meet this 600. Now with that 100 we will not be able to meet this 600, which means somewhere in between we have to place an order for another 500. So on the face of it, if we order a quantity which is, say, in between these two demands, it is quite likely that we end up making one additional order. So if we really want to save that order, it makes it easier to assume that if we order here, we would rather order a 400 or rather order a 1000 and not a number that is in between. So this leads to a very important result, and that result is a Wagner-Witten result, which we have actually seen earlier. So let me repeat those two results. So the optimum solution to this under certain conditions will satisfy two important properties, which is, if I place an order in the beginning of a certain period, then the order quantity will be either the demand of that period or the demand of 2 periods from there or demand of 3 periods from there, and so on. So the order quantity will be a summation of the demand for certain k consecutive periods. Second important property is, I will place an order only when my stock at the beginning of that month is 0. So when the stock is positive, then that stock should be enough for me to meet the demand of the entire month, at least the demand of the entire month. So we look at these two basic ideas and then formulate this problem as an integer programming problem. One could solve it using dynamic programming also, but at the moment let me formulate and solve an integer programming problem for this. So the moment we take care of these two assumptions, that the order is placed at the beginning of the month and the order quantity should be the summation of k months demand, k could be 1 or 2 or 3 from that point. And secondly, we place an order only when the stock is 0. If there is stock at the beginning of that month, then there should be enough stock to meet the requirement of that month. So the moment we assume these two things, which will happen under certain conditions, we now formulate a problem where yi equal to 1, if we place an order in month I, when we say place an order, we mean place an order at the beginning of the month. We still assume instantaneous replenishment. So with the quantity that arrives at that time, we will be able to meet the demand of that month. Now let xi be the quantity ordered. So yi is a binary variable, so it is a 0 1 variable. We either place an order or we do not place an order. Xi is the quantity that is ordered. So the objective function will be to minimize the sum of the ordering cost as well as the inventory holding costs. So we first write the objective function, we write part of the objective function, then we write the constraints, and then we write the remaining portion of the objective function. So objective function will be to minimize the order cost plus carrying cost. So minimize sigma I equal to 1 to 12 300 yi, because every time an order is placed, if yi equal to 1, then we incur 300, which is the order cost. So this is the total order cost component. Plus we also need to have the inventory holding cost for the items. Now here what we are going to do is, we have calculated that Cc is rupees 4 per unit per year. Our period is a month, so Cc has to be written as so many rupees per unit per month. So this will become 4 by 12 or 1 by 3 per unit per month. So the inventory holding cost will be plus 1 by 3 into, now we are going to charge the inventory, we are going to make another assumption that we are going to charge the inventory for the ending inventory in that period. Normally inventory can be charged in two ways. One is you charge it on average inventory, which means beginning inventory plus ending inventory divided by 2, or you could charge it only on ending inventory. So let us assume we are going to charge it only on ending inventory. So let us call I1 plus I1, I2, I3 etc. as the ending inventories. So this is 1 by 3 into I1 plus I2 plus I12. Again we make an assumption that the beginning inventory is 0, we do not have any inventory, which means we have to place an order here. It is also fair to assume that I12 also will be 0. So it is enough to stop this at I11 because we are trying to minimize the cost. So at the end of the 12th period or 12th month we are not going to leave behind an inventory because the cost will be higher if we do so. Only for the sake of completion we write this I12 and let the solution say that I12 is 0, there is no inventory left at the end of the year. So this is the objective function, but right now I have not defined the I1, I2 here because I am going to eliminate the I1 and I2 at some point. Now we have to look at the constraints. So the constraint, the first month constraint will be x1 is the quantity that I order. So it should be x1 greater than or equal to d1. Because it should be greater than or equal to 400 so that I meet the 400th demand. Now the other way of looking at x1 greater than or equal to d1 is, I am just writing it here, this is not an additional constraint, it is going to replace this. If I1 is the ending inventory at the end of the period 1, then I1 is x1 minus d1. Or when we convert this inequality into an equation, you can write x1 minus I1 is equal to d1, which would give us x1 minus d1 is equal to I1. So this is written as, okay, from this we will know that I1 is equal to x1 minus d1. So I am just going to write here as I1 is equal to x1 minus d1. Later we will substitute for I1 here. Now if I take the first 2 months, the quantity that I order in 2 months is x1 plus x2. So what I order in x1 plus x2 now should be greater than the sum of these two demands, which is 1000. I should be able to meet that. So I will have my second constraint, which is x1 plus x2 should be greater than or equal to d1 plus d2. So if I2 is the ending inventory at the end of period 2, then I2 is obviously the difference between d1 plus d2 that has been ordered in the 2 months, I am sorry, x1 plus x2 which has been ordered in 2 months and d1 plus d2 which has been consumed for 2 months. The difference is I2. So I2 will become from here x1 plus x2 minus d1 minus d2. Now the moment we understand these two constraints, the rest of the constraints are easy. The third constraint will be x1 plus x2 plus x3 is greater than or equal to d1 plus d2 plus d3, from which I3 will be x1 plus x2 plus x3 minus d1 minus d2 minus d3. So like this we have 12 constraints for the 12 time periods. This can also be generalized and written in a single constraint, which is of the form sigma x j equal to 1 to I is greater than or equal to sigma dj j equal to 1 to I for I equal to 1 to 12. Which means if we take the first month I, then this will be x1 greater than or equal to d1. Take the second month I equal to 2, so j is summed from 1 to 2, So, x1 plus x2 is greater than or equal to d1 plus d2 and so on. So, there are 12 constraints which are like this. Then we also need to link the x with the y. X is the quantity that is ordered, and we can order an x j or xi in the ith month only if we choose to order, which means the corresponding yi has to be 1 if xi is greater than 0. So, we need to relate the x and y, which is done by the usual constraint, which is xi is less than or equal to big M into yi. So, when yi is 0, which means I choose not to order in this month, then big M into yi will be 0, this will force xi to be automatically 0. If I choose to order in a month where yi equal to 1, then xi could be either 0 or non-zero, which is what we want. So, there are again 12 more constraints like this, which takes care of this part of it. Then of course, we have already defined yi to be binary 0 1, and we may define xi to be an integer, or we can define xi to be a continuous variable. So, let us assume we simply define xi also to be an integer, because by the Wagner and Wheaton idea we will have all xi's to be integers, because these demands are all integers. So, now the constraints are all written in terms of x and y, but the objective function has this I term. So, this I1 has to be replaced in terms of x. So, I1 is x1 minus d1, I2 is x1 plus x2 minus d1 minus d2, I3 is x1 plus x2 plus x3 minus d1 minus d2 minus d3 and so on. So, when we substitute this into the I1 plus I2 plus I3, what we will get is 12 times x1 plus 11 times x2 plus 10 times x3 etc. up to x12, because for I1 you are going to have x1 minus d1, I2 also is going to have x1 plus x2, so it is going to have an x1 term, I3 also will have an x1 term. So, all the 12 will have x1 12 times, so this will become 12 x1. Now, x2 is going to appear from I2 I3 up to I12, so x2 will appear 11 times, x3 will appear 10 times and so on, minus once again we will have 12 d1 minus or plus 11 d2 plus 10 d3 etc. plus d12. The reason is this d1 is also appearing in all the 12 i's, so you will have minus 12 d1, d2 is appearing in 11 terms from I2 to I12, so this will also appear. So, now we have eliminated the i's, the ending inventories, the I variables we have eliminated, and it is also customary in any linear programming or integer programming that if you have a constant term in the objective function, you remove it and then you solve it, and later you can add that constant into it. So, this is a constant term, so we remove this term and then we solve this. So, we can now solve this linear integer programming problem using a solver or otherwise to get the optimum values of x and y. So, there are 12 terms here, 300 into y1 plus y2 up to y12 plus another terms here that represent the inventory holding cost. There are 12 constraints representing the demand, so that the demand in every period is met. There is no shortage, therefore, no shortage cost is added in the objective function. This model does not allow shortage or back ordering, plus of course the linking constraints between x and y. So, when we solve this optimally, we will get a solution which is this. So, the solution to this will be y1 equal to y3 equal to y5 equal to y6 equal to y8 equal to y9 equal to y11 equal to 1. So, the solution says that we will order in months 1, 3, 5, 6, 8, 9 and 11. So, 7 out of the 12 months we will order. What are the order quantities? Of course, the solution would also throw the excess as a variable which will be there, but the moment we know the y's we also know the x's, because I am placing an order here, I am placing an order here at y3, placing an order at y5, placing an order at y6, placing an order at y8, placing an order at y9, and I am placing an order at y11. So obviously my order quantities are x1 equal to 1000, because I am not ordering in this month, I am not ordering here. So the order quantity here is the sum of these two. X3 is 1800, X5 is 1200, X6 is 1700. The 1700 comes because I have to order for this 900 plus another 800, so 1700. X8 is 1000, X9 is 1900, and X11 is 1400. Now what is the total cost associated with this system? Total cost would be given by the objective function value here. This would be the objective function value, plus of course that constant has to be added. So what we will do now is we will compute the total cost. So there are 7 orders here, so 7 into 300. The inventory holding cost is plus 1 by 3 into, now here we order 1000, at the end of this month we carry 600, so 600 is carried. Now here it is 0, so we order 1800, so we carry another 800 here. Now here we order 1200, we consume all the 1200 here. Here we order 1700, we consume 900, so we carry another 800 here, so plus another 800. We order 1000, we consume all 1000, we order 1900, we consume 1200, so balance of 700 is carried, which is consumed at the end of this period. So we order 1400, 600 is consumed here, 800 is what is carried, so 800. It is also interesting and obvious to note that there are 7 periods where there is an order, there are 5 periods where there is inventory holding, making up for the 12. So total cost will be 2100 plus 6 plus 8 14 plus 8 22, 29 plus 8 37, 3700 by 3, which is so 2100 plus 1200 and 33.33, which is 3333.33. So while writing this formulation, I had mentioned that the objective function has 2 terms. One is the order cost term and the other is the inventory carrying cost term. So while writing the formulation, I mentioned that the inventory cost can be calculated either based on the ending inventory or based on the average inventory. Now this expression was written when we wrote it for the ending inventory in mind. So we defined I1, I2 up to I12 as the ending inventory in the 12 months, and then we simplified it to 12x1 plus 11x2 plus etc. minus a constant. And then we removed the constant because in any mathematical programming problem, when you optimize a function, if there is a constant in the objective function, you can remove it and then you can optimize only the terms containing the variables. Now what we will do is we will try and see what happens if we write this inventory term, the carrying cost term, considering the average inventory and not considering the ending inventory. Now does the solution change if we do that? So let us go back and try to first compute this term or write the equivalent of this term if we consider average inventory and not the ending inventory. So let us write that portion here. So to begin with, we will assume that I1, I2 up to I12 are the 12 values of the ending inventory. So 12 values of the ending inventory are I1, I2 up to I12. Now if we take the first period, the beginning inventory is 0. So the order quantity is x1. So beginning inventory now will be 0 plus x1, which is x1 in the first period. Now at the end of the period, the ending inventory at the end of period 1 is I1. Now we order x2 in the beginning of period 2. So beginning inventory will be I1 plus x2. Now for the third period, the ending inventory will be I3, but the beginning inventory will be I2 plus x3, because I2 is the inventory that is available at the end of period 2, and at the beginning of period 3 we are adding an x3. So I2 plus x3 is the beginning inventory for period 3, I3 is the ending inventory for period 3. So this way we can write all the beginning inventories and ending inventory term, and for the 12th month beginning inventory will be I11 plus x11. So the average inventory for month 1 will be x1 plus I1 divided by 2. The average inventory here will be I1 plus x2 plus I2 divided by 2, and one more term it will be I2 plus x3 plus I3 divided by 2, and for the 12th period it will be I11 plus x11 plus I12 . The 12th period, the beginning inventory will be I11 plus x12, because x12 is the quantity that we order. So this will become I11 plus x12. So this will become I11 plus x12 plus I12 divided by 2. So if we sum all the average inventories, we will get the I1 plus 2 appears here, I1 plus 2 also appears here. Similarly, I2 divided by 2 appears here, I2 divided by 2 appears here. So when we take only the I1, I2 up to I12 terms, we will have I1, because I1 divided by 2 plus another I1 divided by 2. So I1 plus I2 plus up to I11. The I11 will have a term from the previous, apart from the previous term and apart from here. I12 does not have a succeeding term because that is the last period. So up to I11 plus we will have I12 divided by 2, and then we are going to have x1 by 2 plus x2 by 2 plus x3 by 2 up to x12 by 2. So this will be plus x1 plus x2 plus etc. plus x12 divided by 2. Now what we need to do is to write this I12 divided by 2 in terms of, first write I12 and then substitute for I12 to see what happens. Now what is I12? I12 is the inventory at the end of the 12th period. Beginning inventory is 0 here. So I12 is in principle sigma x1 plus x2, or sum of x1 plus x2 up to x12, which is what we have procured, minus D1 plus D2 to D12, which is what we have consumed. So, I12 will now be equal to, I12 is x1 plus x2 plus x12 minus D1 plus D2 up to D12. So, let me write this as sigma x and let me write this as sigma d. So, I12 divided by 2 is equal to sigma x divided by 2 minus sigma d divided by 2. So, this will become I1. So, the sum of the average inventory will be I1 plus I2 up to I11 plus this I12 divided by 2 is sigma x by 2 minus sigma d by 2, this is another sigma x by 2. So, this will become plus sigma x minus sigma d, because there is a sigma x by 2 term that comes out of this, this is another sigma x by 2 term. So, they add up to give you sigma x minus sigma d. Now, we need to go back, we can actually look at it in two ways, but the more mathematical way is to try and define what are these I1, I2 up to I11 and then see what they are. Now, what is I1 plus I2? I1 is x1 minus d1, I2 is x1 plus x2 minus d1 minus d2 and so on. Then plus sigma x minus sigma d. Now, this no, you get I1 plus I2 plus I11, which is what I am writing. I1 is x1 minus d1, I2 is x1 plus x2 minus d1 minus d2. No, the total inventory is this term is what I am writing here. Now, this term is I1 plus I2 up to I11 plus I12 by 2. Now, this portion I12 by 2 is written as this. So, this portion is up to this portion is, this is here plus I12, let me write from here so that there is no confusion. So, up to I11 I am writing from here. Now, this portion is I12 by 2 plus sigma x by 2. Now, I12 by 2 is sigma x by 2 minus sigma d by 2 plus sigma x by 2. So, there is a by 2 that comes here. So, this will become x1 minus d1 plus x1 minus x2 minus d1 minus d2. We get up to 11 terms. So, the 12th term will not be there. So, the 11th term will be x1 plus x2 to x11 minus d1 minus d2 up to minus d11. So, this on simplification will give this x1 will come 11 times. So, this will give me 11x1 plus 10x2 plus 9x3 etc. up to x11. Now, this one will become minus 11d1 minus 10d2 minus 9d3 and so on minus d11. Once again this term will repeat. So, plus sigma x minus sigma d divided by 2. Now as far as we are concerned, minus 11 d1 minus 10 d2 minus 9 d3 up to minus d11 is a constant. This is also a constant. So this is 11x1 plus 10x2 plus 9x3 up to x11. Sigma x is x1 plus x2 plus x3 up to x12. So when we add it, we get 12x1 plus 11x2 etc. plus x12 minus a big constant k. So we have to write, if we write average inventory term and bring it back to this expression, we should write 1 by 3 into 12x1 plus 11x2 plus 10x3 plus x12 minus some very big k constant. And based on the same idea, we can remove this constant and we can solve it. So as far as the optimization is concerned, even when we look at average inventory, which is taken as beginning inventory plus ending inventory divided by 2, we get the same optimization problem, except that the constant that we are subtracting is slightly different. There is another way of looking at the same thing. The reason perhaps is that if you see this, initially we started with ending inventories as I1 plus I2 plus I3 up to I12 is what we had. Now ordinarily we will have I12 will be 0 because beginning inventory is 0, pushing an I12 will lead to higher cost, so I12 will be 0. So it is enough if we do up to I11. And by the same reason we will realize that sigma x will be equal to sigma d, because when the initial inventory is 0 we will not buy and then finally keep it as final inventory. So this term will essentially become a constant. So average inventory would also lead us to the same value for ending inventory. So we have already seen the optimum solution to it, the problem does not change, so this is the solution for it. The only change is in our calculating the total cost. Now when we considered ending inventory, the total cost was computed for order cost plus carrying cost of the ending inventory. Now what we have to do is we have to compute this cost again considering the average inventory, and there will be 12 terms instead of 5 terms. The 5 terms came here because we ordered for 7 periods, which meant that 5 periods demand was carried. So when we computed based on ending inventory, we got 5 terms here. Now when we compute it based on average inventory, we will have 12 terms here. So let us compute those 12 terms again and see what happens to the total inventory cost. So there are 7 orders, order cost is taken as 300, so 7 into 300 plus 1 by 3 is our CC, 4 per unit per year becomes 4 divided by 12 per unit per month, so 1 by 3 per unit per month. So now what do? We start the first month by ordering 1000. So first month beginning inventory is 1000. So let me write down the points what we order using a different color, perhaps yellow. So we will have 1000 ordered here, Y3 is 1800, this is 2100, I am sorry 1200, 1700, 1000, 1900, 1400. So first month beginning inventory is 1000, ending inventory is 600, so 1000 plus 600 divided by 2 is 800. Second month beginning inventory is 600, ending inventory is 0, so average inventory is 300. Third month beginning inventory is 1800, ending inventory is 800, so 2600 divided by 2 is 1300. Fourth month beginning inventory is 800, ending inventory is 0, so you get 400. Fifth month 1200, ending inventory is 0, so we get 600. 6th month 1700 plus 800 divided by 2, so 1250. 7th month will be 400, 8th month will be 500, 9th month is 1900 plus 700 divided by 2, 1300, 10th month is 350, 11th month is 1100 and 12th month is 400. Now 400 comes, 1100 comes because we order 1400. At the end of this month ending inventory is 800, 1400 plus 800 is 2200 divided by 2. So this will become 2100 plus, now let us add only the 50 terms first. 1250 plus 350 is 1600, 2400, 2700, 4000, 4400, 5000, 5400, 5900, 6200, 7200, 8300 plus 400 is 8700 divided by 3. So this is 2900 plus 2100, which is 5000 will be the optimum, the value of the objective function at the optimum if we consider the average inventory. So the important assumptions, for a quick recap, the important assumptions are that the Wagner and Witten assumption that we place an order when the inventory is 0, and when we place an order for that period or sum of demands of certain k number of periods. When there is inventory at the beginning of the period, we will not place an order, and that inventory should be enough to meet at least this month's demand, and in principle to meet the demand of an integral number of months starting from now. So under those two assumptions we formulated this problem. Problem could also be solved by dynamic programming, but we solved by integer programming by defining yi as binaries. Now let us make a very quick comparison with what we know. Now let us go back and take this 10,000 as the annual demand. The important deviation of this problem from the economic order quantity problem is that the demands are now given over 12 periods, whereas there the annual demand of 10,000 was given as an annual demand, and the demand is the same at every instance of time. Now demand varies here. The original EOQ we assumed an infinite horizon, now there is a finite horizon of 12 time periods. Nevertheless, let us make a comparison. Now just in case we have taken this 10,000 as the annual demand and then use the economic order quantity formula to find out the economic order quantity and the associated total cost, what happens. So when we do that, so we could write D equal to 10,000, C naught equal to 300, Cc equal to 4 per unit per year. Now Q is equal to root over 2 D C naught by Cc, which we have already calculated in an earlier lecture, 1224.74, and then we also know that the total cost for this is root over 2 D C naught Cc, which will give us 4898.98. Now we have to first understand this is an optimal solution to an integer programming problem under certain assumptions, which gives us 5000. The best value of economic order quantity, assuming that this is an annual demand of 10,000, is 4898.98, and it is slightly less than that 5000. It is very clear as to why this was marginally higher. That is because this problem is further constrained. This problem is further constrained by many reasons. Now there is this has a finite period, this has an infinite period, that has demand that varies with time, here you have demand that does not vary with time. So in principle that is a further constrained problem, so it gives us 5000. But then why should we not use this if this is usable? Now let us go and see why we need this and why we will not be able to use this. Now to do that, let us go back and find out if the order quantity is 1224.74, then the number of orders per year n will be 10,000 divided by 1224.74, and we quickly compute that to be 8.2. So let us call it 8.2 orders, actually 8.17, let us call it as 8.2 orders. Now there are going to be 8.2 orders over 12 months, so let us call the ordering frequency per month, how many orders is 12 divided by 8.2, which is roughly about 1.5. Let us approximate it to about 1.5 orders per month. 8.2 orders over 12 months, then we have an order every 1.5 months, an order every 1.5 months per order. Now for example, we are going to order, let us say 1224.74, let us kind of approximate it to 1225, which is not a very wrong approximation. So we first order 1225. Now let us try and see what we do with this. So we can meet the first month's demand of 400 through it. So at the end of the first month we will have 825. But then somewhere in between, we after 0.5 months we will have another 1225 coming in. So the second month's 600 we can actually meet, but somewhere in between we will get the 1225 that comes in. So at the end of it we will have 225 plus 1225. So we will have 1225 plus 225, which is 1500. So at the end of the second month we will have 1000, every 1.5 months we place an order. So we will have 1500, this is beginning of the first month, so end of first month, end of second month we will have 1500. Now we meet this 1000 here, so we would have 500 at the end of this month. Now halfway, the next order is going to come half of now the first order has actually come here, the second order will come at this point. So 500 plus 1250 will be 1750 will be the order. So we will have 1750 here at the end of 3, that will be the inventory at the end of 3 and so on. So actually we would realize that we will be able to meet the entire demand by doing this. Actually we will be able to do that in this case. If we continue this kind of calculation, we will be actually able to show that we can meet the 12 months demand by suitably ordering this. There are no issues on that. The only place why, even though this will be a feasible solution, if we show this will be a feasible solution with cost equal to 4898.98, but then the optimal solution here will ask us not to order somewhere in the middle here and so on. The optimum solution will ask us to order at these points with a slightly higher 5000. So we need to explain why that difference happens. Essentially the difference happens because when we made this calculation was based on a total cost TC is equal to D by Q C naught plus Q by 2 CC. Now the average inventory there was taken as Q by 2, that comes from here, which was based on the assumption that the demand is D in every instance. Now the moment we look at problem with time varying demand this way, the demand is not D at every instance, the demand is different. Therefore, the correctness of Q by 2 as representing the average inventory comes into question. So Q by 2 is not a correct estimator of this. Therefore, if we use this Q by 2 instead and then optimize, the optimization portion is right, differentiating and setting it to 0 and getting it is right, but Q by 2 into CC is not the correct way to represent the average inventory. And because the average inventory was represented in an incorrect way here, it ended up giving us a 4898.98. Whereas the best way to do it is the way we have done it in this formulation, to get this answer, to get a value of 5000. So using the economic order quantity per se and implementing it, even though it is implementable, as in this example it is implementable, it is fine, but then the correctness of the average inventory will come into the question, and when we actually correct this term for the solution which is 1225 every 1.5 months, and if we correct the term while doing this calculation, we correct this term when we do this calculation, then you realize, for example, that the average inventory would not be Q by 2, it will be something slightly more, which would eventually give us a number that is slightly more than 5000. So we need to use this method when we actually work with problems on time varying demand and not approximate the economic order quantity. Now another area where the economic order quantity can suffer is this. Now suppose instead of the total demand, let it be 10,000, but then if we say that the first period's demand is not 400, but for the sake of argument, if the first period's demand is itself is 2000. Now the rest of the demands are such that the total annual demand is 10,000, which means the demand for the remaining 11 periods on summation is actually 8,000, so that the total demand becomes 10,000. Now instead of using this model, which is the Wagner-Witten algorithm, if we had gone by the economic order quantity and said we would use it, then the economic order quantity tells you to order 1224.74, the same thing based on the same 10,000. So we initially begin with 1224.74, and then our next order is going to happen after 1.5 months because of this 8.2 and 1.5 months. So if we assume that in the first day of January you have ordered 1225, and your next order you are going to make around 15th of February, which is 1.5 months from now. So you have to meet the 1.5 months demand with the 1225 that you have. Now you won't be able to do that because the first month's demand itself is 2000. So we will be forced to have shortage, and then we have not included shortage in doing this. So for another reason you cannot directly use the economic order quantity formula and then say that I will suitably modify it to take care of time varying demand. In an example like this, where it is not, you do not have a real peak, 1 month taking a demand of 2000 while the other 11 months having a demand of 8000 clearly shows there is a peak here. Whereas if we look at these numbers, you see that they are reasonably spread out around the average value of 1000 or slightly less. The average value of 833, it's kind of spread out, even though you have a 1200 somewhere here. But if one of the demands shows a peak, then implementing a modification of the economic order quantity would lead us to shortage. Therefore this approach is not recommended, while this approach is recommended. Now having seen this, let us look at just a couple of more instances of this. One is this problem is formulated and solved as a integer programming problem, where the yi's were binary variables and xi were defined as integers. I also mentioned a little earlier that it is not necessary really to keep them as integers because the demands themselves are integers, but the yi's have to be binary. Now this would require an integer programming solver, and if we are doing it for large time periods, integer programming may take a little longer than we normally anticipate, and we may require more sophisticated solvers. So the question is, can we try and solve this problem heuristically and not really worry about the optimal solution, but try and get a good near optimal solution. Second issue that comes is, now this integer programming formulation can be made if we have a finite number of periods. If we have a situation where we do not want finite time period, if we look at practice about demand of a particular item, and let us say the forecasting happens continuously, and then there is a rolling kind of a forecast where initially the forecast is made for 1 year, and then after a quarter, after 3 months, the forecast is made for another 1 year. Therefore the forecast is rolling, and in some sense there is no end to this number. So if there is no end to this number, we cannot make that formulation, because that formulation is for a finite time period. So the question is, how do we extend this to look at situations where we do not have finite time periods? Now can we solve that optimally? The answer is no, because we need to know how many periods, all these are summations. So you need to know how many periods you require. So in order to handle situations which are more practical, where the time period is not fixed and defined, we need to look at heuristics which give good solutions comparable to this optimum solution. So we look at a couple of such heuristics in the next lecture.